Imagine stepping outside on a crisp morning, the sky above you a vast and silent clock. There are no notifications buzzing in your pocket, no digital reminders, just the steady movement of the sun, the moon, and the stars. For ancient peoples, this celestial dance wasn't just something beautiful to observe, it was the very heartbeat of existence. Their survival depended on reading these patterns accurately, on knowing precisely when to plant, when to harvest, when to celebrate, and when to prepare. Long before the first written word, humanity was already looking upward, trying to make sense of time itself. What they accomplished with nothing but stone, sky, and sheer determination remains one of history's most profound and enduring mysteries. Across continents and cultures, from the sun-scorched deserts of Egypt to the dense rainforests of Central America, our ancestors engineered astonishingly precise calendars that tracked the year with near-perfect accuracy. They built megalithic monuments that captured the sun's rays on the solstices, designed temples aligned with the rising of specific stars, and developed mathematical systems so advanced they could predict eclipses centuries into the future. These were not just practical tools, they were expressions of a deeper human yearning to find order in chaos, to weave the passage of days into stories of meaning, ritual, and shared identity. The calendar builders of the ancient world were among the first scientists, the first engineers, and the first poets of time. In this video, we'll journey back thousands of years to uncover how these incredible innovations came to be. We'll stand in the shadow of Stonehenge as the sun aligns with its massive stones, walk the banks of the Nile where priests tracked the flood season by the star Sirius, and climb the steps of Mayan pyramids designed to cast serpent-like shadows on the equinox. We'll explore not only the how but the why, how timekeeping shaped empires, guided explorers across oceans, and even influenced the myths and religions that still resonate today. This is a story about humanity's oldest and most universal quest to understand our place in the cosmos. So settle in, and let's unravel the secrets of how ancient cultures shaped time with nothing but stone and sky. Picture a world where your next meal depends on knowing exactly when the rains will come, or when a specific herd of animals will pass through the valley. For our earliest ancestors, this wasn't just a matter of convenience, it was survival itself. Before cities, before writing, even before farming took hold, humans were already deeply attuned to the rhythms of nature. They watched the moon's phases to track the best times for hunting under cover of darkness, observed the subtle shifts in star patterns that hinted at changing seasons, and learned to read the environment like a living, breathing calendar. This fundamental connection to natural cycles formed the very bedrock upon which all later timekeeping would be built. As societies transitioned from nomadic hunting and gathering to settled agriculture, the stakes became even higher. A miscalculation in planting time could mean starvation for an entire community, while missing the signs of an approaching winter could prove fatal. The development of the first formal calendars emerged from this pressing need to predict and prepare. Early farming communities noticed that certain celestial events like the sun reaching its highest or lowest point in the sky reliably corresponded with seasonal changes. They began marking these moments with simple stone arrangements, notched bones, or wooden poles, creating the first physical representations of time's passage. These primitive markers gradually evolved into more sophisticated systems that could track longer periods and more complex cycles. But calendars served far more than practical purposes. They became powerful tools for social organization and cultural identity. In ancient Mesopotamia, temple priests used lunar calendars to schedule religious festivals that reinforced community bonds and affirmed their authority. The Egyptians aligned their calendar with the annual flooding of the Nile, which not only dictated agricultural cycles but also determined tax collection and labor obligations. By creating shared temporal frameworks, these early societies could coordinate activities across vast distances, plan large-scale projects, and establish common rituals that strengthened social cohesion. Timekeeping became a way to weave individual lives into a larger collective story. The development of calendars also represented humanity's first major step toward scientific thinking. Early astronomers, often priestly classes or specially trained observers, began systematically recording celestial patterns over generations. They noticed inconsistencies between lunar cycles and solar years, leading to innovations like intercalation, the addition of extra days or months to keep calendars aligned with seasons. This required not only careful observation but mathematical reasoning and the ability to think across generational timescales. The very act of calendar making pushed human understanding forward, transforming random observations into predictable patterns that could be quantified and shared. Perhaps most profoundly, these early timekeeping systems allowed humans to conceptualize time itself as something measurable and manageable. Rather than being at the mercy of unpredictable natural forces, communities could now anticipate changes, plan for the future, and preserve knowledge across generations. This psychological shift from passive observation to active measurement represented a revolution in human consciousness. It laid the foundation for everything from urban planning and architecture to literature and philosophy, enabling the complex societies we recognize as civilization today. The humble beginnings of timekeeping remind us that our modern relationship with time, for all its digital precision, still rests on these ancient foundations of observation, necessity, and the human drive to make meaning from the patterns of the cosmos. Now, let's travel northwest to the windswept Salisbury Plain in England, where one of the world's most iconic and enigmatic monuments stands as a testament to ancient ingenuity. Stonehenge, with its massive sarsen stones arranged in a mysterious circular pattern, has captivated the human imagination for centuries, but beyond its imposing presence, this megalithic marvel functioned as a sophisticated astronomical observatory and calendar, meticulously aligned with the movements of the sun. On the summer solstice, the longest day of the year, the sun rises directly over the heel stone, its rays streaming through the monument's central archway to illuminate the altar at its heart. Conversely, during the winter solstice, the sun sets perfectly framed within the great trilithons, marking the year's shortest day and the symbolic rebirth of the sun. These precise alignments were not accidental. They required generations of careful observation and an intimate understanding of the solar cycle. The construction of Stonehenge was a monumental undertaking that spanned over 1,500 years, evolving from a simple earthwork enclosure to the complex stone structure we see today. The largest of these sarsen stones weigh up to 30 tons and were transported from quarries over 20 miles away. Without the wheel or metal tools, builders used sledges, ropes, and sheer human labor to move these giants. They then shaped them using stone hammers and fitted them together with complex joints, a technique more commonly associated with woodworking. This incredible feat of engineering suggests a highly organized society with specialized knowledge, capable of planning and executing projects that would span multiple human lifetimes. The very act of its construction was an intergenerational commitment to capturing time in stone. While its solar alignments are the most famous, Stonehenge likely tracked other celestial events as well. Some researchers propose that the 56 Aubrey holes, circular pits surrounding the monument, could have been used to predict lunar eclipses by moving markers in a complex pattern. Others suggest that certain alignments may have corresponded with the movements of stars important to the builders' cosmology. This points to a holistic understanding of the heavens, where the sun, moon, and stars were all part of a connected cosmic clock. The monument served as a permanent record of celestial knowledge, a way to fix the cyclical patterns of the sky into the immutable landscape of the earth, ensuring that this critical information for survival and ritual would be preserved for future generations. The purpose of Stonehenge extended far beyond mere practical timekeeping. It was a sacred space deeply woven into the spiritual and social fabric of Neolithic Britain. As a place of pilgrimage, it would have drawn people from across the region for major seasonal gatherings. These events were crucial for reinforcing social ties, exchanging knowledge and goods, and performing ceremonies that ensured community prosperity and harmony with the cosmos. The solstice gatherings were not just about marking a date on a calendar. They were powerful communal experiences that connected people to the rhythms of nature, to their ancestors who built the monument, and to each other. The alignment of the stones created a dramatic theater for these rituals, where the sun itself became a participant in the ceremony, validating the authority of spiritual leaders and unifying the community through shared awe. What makes Stonehenge so profoundly impressive is that this complex understanding of astronomy and this mastery of engineering were achieved by a pre-literate society. They encoded their knowledge not in written texts but in the very arrangement of the land and stone. This architectural language speaks to a different way of knowing, one based on oral tradition, meticulous observation, and a deep, embodied connection to the environment. The enduring mystery of Stonehenge challenges our modern assumptions about technology and progress. It stands as a powerful reminder that intellectual achievement and scientific curiosity are not solely the domain of civilizations with writing, but are fundamental parts of the human story, etched into the earth itself long before the first word was ever written on a page. While the builders of Stonehenge were mastering the solar cycles of Northern Europe, an equally profound relationship with time was developing along the banks of the Nile. For the ancient Egyptians, time was not an abstract concept but a force of life itself, measured by the one event that dictated their survival, the annual flooding of the river. Each year, the Nile would overflow its banks, depositing a layer of rich, black silt that transformed the desert into a fertile oasis. Predicting this event was a matter of feast or famine, and so they turned their eyes to the heavens, discovering a celestial herald that never failed them, the star Sirius. Known to the Egyptians as Sopdet and to the Greeks as Sothis, Sirius would disappear below the horizon for about 70 days each year. Its reappearance just before dawn in mid-July, an event called the Heliacal Rising, coincided almost perfectly with the beginning of the Nile's inundation. This was no mere coincidence to the ancient priests. It was a divine signal, a promise from the gods that the life-giving waters were on their way. This celestial correlation became the absolute cornerstone of their timekeeping system, anchoring their entire calendar to this one critical astronomical event. The first day of the Egyptian New Year was the day Sirius was seen rising with the sun. From this foundation, they developed one of history's first solar calendars, a remarkably simple and effective system of 365 days. They divided their year into 3 distinct seasons, each 4 months long, that reflected the rhythm of the river and the land. Akhit, the season of inundation when the Nile flooded the fields. Peret, the season of emergence when the waters receded and farmers could sow their seeds in the moist, fertile soil. And Shemu, the season of harvest, the dry period when crops were gathered. Each month consisted of 30 days, and to complete the solar year, they added 5 extra days at the end, known as the epagomenal days. these were considered outside the normal year, a time of danger and celebration dedicated to the gods, particularly the birth of Osiris, Isis, Set, Nephthys, and Horus. But the Egyptian innovation didn't stop there. They were masterful architects of time in a literal sense, transforming their entire landscape into a colossal timekeeping device. Towering obelisks, often capped in electrum to catch the first and last rays of the sun, functioned as giant sundials, their moving shadows marking the passage of hours across precisely laid temple courtyards. The very design of their temples often served astronomical purposes. Certain corridors and sanctuaries were aligned so that on specific days of the year, like the solstices or the new year, beams of sunlight would travel down the axis to illuminate the statue of a god deep within the inner sanctum. This wasn't just architecture, it was a physical manifestation of their belief that cosmic order, or mat, was reflected in the perfect, predictable cycles of the heavens. This seamless integration of astronomy, agriculture, and religion created a profound sense of stability and order that helped Egyptian civilization endure for 3,000 years. The calendar dictated not only when to plant and harvest, but also when to hold festivals, when to crown a pharaoh, and when to conduct rituals to ensure the continued favor of the gods. The pharaoh, as the intermediary between the divine and the earthly, was responsible for maintaining this cosmic harmony. A well-predicted and prosperous flood season reinforced his divine right to rule, while a miscalculation or a poor flood could be seen as a failure to uphold Mat. The Egyptian calendar was therefore more than a tool. It was the very framework of their reality, a sacred cycle that connected the rhythm of the stars to the pulse of the river and the heartbeat of their society. While the grand solar alignments of Stonehenge and the Nile stellar prophecies represent incredible feats of long-term timekeeping, the very first calendar most cultures ever used was far simpler and more intimate, written not in stone but in the night sky itself. The moon, with its clear, consistent, and highly visible cycle from dark to full and back again, provided the most natural and accessible clock imaginable. Its 29-and-a-half-day journey across the heavens became the foundational unit for countless ancient societies. The month. This rhythm was impossible to ignore, a silent pulse in the darkness that organized life into manageable, repeating segments. For cultures like the Babylonians, who left some of the most detailed early records, the new moon held particular significance. The first sighting of a thin crescent sliver after a period of darkness was a moment of public announcement and often religious celebration. This marked the official start of a new month. They didn't just count days, they named each lunar phase, understanding its practical implications. The waxing moon, growing brighter each night, was a time for action, expansion, and undertaking new ventures. The full moon provided the best light for nighttime activities, from hunting and traveling to holding communal gatherings. The waning moon, with its diminishing light, was often associated with introspection, completion, and release. This lunar rhythm was woven directly into the fabric of social and economic life, dictating the timing of markets, the scheduling of legal proceedings, and the dates of important religious festivals dedicated to various lunar deities. The advantages of a lunar calendar were immediately apparent to early societies. Its cycle is short enough to be easily observed and tracked without any specialized tools. One simply had to look up. This made it a universal system, independently developed by cultures from the islands of the Pacific to the forests of northern Europe. Coastal communities quickly learned to connect the moon's phases with the ocean's tides, allowing them to predict the best times for fishing, gathering shellfish, or launching boats. Hunter-gatherers could plan expeditions around the light of the full moon, while agricultural societies, though more tied to the solar year, still used the moon's phases to schedule the finer details of planting, tending, and harvesting within the broader seasons. However, this elegant system had one critical flaw: a fundamental mismatch with the agricultural reality governed by the sun. 12 lunar months only add up to about 354 days, leaving a deficit of roughly 11 days compared to the 365-day solar year that dictates our seasons. If left uncorrected, a purely lunar calendar would drift rapidly against the backdrop of the seasons. A festival celebrating the spring harvest would, within just a few years, be occurring in the dead of winter. This presented a massive problem for agricultural societies whose survival depended on precise seasonal timing. The ingenious solution to this problem was a concept known as intercalation, the periodic insertion of an extra month into the calendar to resynchronize the lunar and solar cycles. The Babylonians, masters of this practice, developed a sophisticated 19-year cycle that included 7 intercalary months, a system so accurate it kept their lunar calendar in near-perfect harmony with the solar year for centuries. This was no small feat. It required dedicated, long-term astronomical observation and a developing understanding of mathematics. The very need to fix this drift forced ancient astronomers to think more critically about the mechanics of the cosmos, pushing them from simple observation toward true predictive science. This challenge, born from the moon's imperfect fit with the sun, became a powerful engine for innovation, setting the stage for the more complex lunisolar and purely solar calendars that would follow. While the moon offered a convenient monthly rhythm, ancient cultures soon realized that the true key to their survival, the changing of the seasons, was written in the far grander and more consequential journey of the sun. This shift in focus from lunar to solar timekeeping marked a monumental leap in human understanding, moving from tracking brief cycles to grappling with the immense scale of the solar year. The sun's path across the sky is anything but constant. It shifts north and south throughout the year, rising and setting at different points on the horizon. Its highest arc and longest presence in the sky heralds the summer solstice, a time of peak warmth and growth, while its lowest, weakest arc on the winter solstice signals the year's symbolic death and eventual rebirth. Precisely halfway between these two extremes lie the equinoxes, the 2 days of perfect balance when day and night are of equal length. It was these 4 celestial pillars, the 2 solstices and 2 equinoxes, that became the foundational anchors for the solar calendar, providing a rock-solid framework for organizing the entire year. To capture these solar events with precision, ancient astronomers turned their architectural genius to the landscape itself. They engineered structures that functioned with the reliability of a modern clock, using light and shadow as their indicators. In the American Southwest, the ancestral Pueblones carved spiral petroglyphs onto cliff faces. On the summer solstice, a single dagger of sunlight would pierce a carefully placed opening in the rock, bisecting the center of the spiral in a breathtaking display of accuracy. This sun dagger was more than just a spectacle. It was a critical agricultural alert, signaling the time for planting or the imminent arrival of the monsoon rains. Similarly, across the Atlantic, the Great Passage Tomb at Newgrange in Ireland was designed so that on the winter solstice, the dawn sun would flood its long, dark entrance tunnel with a beam of light, illuminating the inner chamber for just 17 minutes. This dramatic event, representing the triumph of light over darkness, was likely a powerful spiritual moment that reaffirmed the cycle of life and death for the entire community. The primary advantage of the solar calendar was its unwavering correlation with the environment. Unlike the lunar cycle, which drifts through the seasons, the solstices and equinoxes are fixed to the Earth's tilt and orbit, making them perfectly reliable markers for seasonal changes. This stability was a game-changer for complex agricultural societies. Knowing the exact date of the spring equinox could determine the optimal window for sowing seeds, ensuring the best possible yield. Predicting the autumn equinox told communities exactly when to begin the harvest to avoid early frosts. For pastoralists, the sun's cycle dictated the movement of herds to summer and winter grazing grounds. This precision allowed for advanced planning, surplus storage, and the support of larger, more complex populations. The solar calendar didn't just mark time, it managed risk and guaranteed prosperity. However, this new precision came with its own formidable challenge: the inconvenient truth that the solar year is not a neat 365 days. It is approximately 365¼ days long. This tiny fraction, a mere 6 hours each year, might seem insignificant, but over centuries it accumulates into a major problem. Without correction, a calendar that assumes a 365-day year will slowly fall out of sync with the actual seasons. After 120 years, the calendar would be off by about 30 days, meaning a spring festival would eventually be celebrated in the heat of summer. Correcting this drift became the holy grail of ancient astronomy, requiring not just observation but sophisticated mathematics and long-term record-keeping. The pursuit of a perfectly accurate solar year drove incredible intellectual innovation. The Egyptians were among the first to formally adopt a 365-day civil calendar, though they understood it was imperfect. Later, the Romans, under Julius Caesar, consulted Alexandrian astronomers to introduce the Julian calendar, which incorporated a leap year every 4 years to account for that extra quarter day. This was a massive step forward, though it too was slightly too long, an error that would eventually prompt the Gregorian reform over a millennium and a half later. This centuries-long project to refine the solar calendar represents one of humanity's earliest and most sustained scientific endeavors, demonstrating a profound commitment to aligning human civilization with the fundamental rhythms of the cosmos. Yet while the sun and moon governed the daily and seasonal rhythms of life, ancient sky watchers soon turned their gaze to a far more constant and enduring clock face: the fixed stars and wandering planets. This was a shift in perspective from the immediate to the eternal, from tracking seasons to mapping the grand, multi-generational cycles of the cosmos itself. Unlike the sun, which rises and sets in a daily blur, the star-filled night sky changes with a stately, almost imperceptible slowness. The same constellations return night after night, but over centuries, their positions relative to the horizon slowly drift due to a wobble in Earth's axis known as precession, a cycle that takes 26,000 years to complete. To notice this, let alone measure it, required a tradition of observation spanning hundreds of generations, a testament to the incredible long-term dedication of these early astronomers. This stellar perspective allowed cultures to operate on a timescale that dwarfed human lifespans. The Maya, for example, were unparalleled masters of this long-count timekeeping. They didn't just track the sun and moon, they meticulously charted the movements of Venus, which they saw as a powerful and often dangerous deity. Their Venusian calendar was precise to within 2 hours over a 500-year period. The appearance of Venus as the morning star was associated with war and upheaval. Maya rulers would often schedule military campaigns and ritual ceremonies to coincide with its specific phases, believing the celestial omen would grant them favor. This wasn't astrology in the modern sense, it was a complex integration of precise astronomy with statecraft and religion, where the timing of human events was synchronized with the undeniable clockwork of the planets. On the vast, open ocean, another culture developed a completely different but equally profound relationship with the stars. For the Polynesian voyagers who settled islands scattered across millions of square miles of the Pacific, the stars were not just markers of time but a literal navigation system. They memorized the precise rising and setting points of key stars and constellations on the horizon, creating a mental star compass. They knew that just as the sun rises in the east and sets in the west, each star would rise at its own specific point, travel across the sky, and set at a predictable location. By memorizing hundreds of these celestial pathways, a master navigator could hold their position on the featureless sea, knowing that steering toward where a certain star would rise would lead them to a specific island group. Their calendar was a living, moving map written in the heavens, guiding them across time and space. This deep stellar knowledge also unlocked the ability to predict rare and awe-inspiring events that must have seemed like moments of cosmic chaos. By understanding the long-term cycles of the moon and the predictable paths of the planets against the backdrop of stars, cultures like the Babylonians could forecast eclipses with remarkable accuracy. The ability to predict when the sun or moon would dramatically disappear from the sky transformed a terrifying omen into a demonstration of priestly power and cosmic order. It showed that even the most shocking celestial events were part of a predictable pattern, a reassurance that the universe, though vast and powerful, operated by knowable rules. Comets, too, while seemingly random to the untrained eye, were sometimes recorded in annals that allowed priests to recognize patterns or cycles across centuries. By anchoring their calendars to the fixed stars, ancient cultures were effectively building cathedrals in time structures meant to endure for millennia. A king might commission a temple aligned to a star whose slow drift would only become apparent to his descendants 1,000 years later. A myth might be written about a hero placed in the sky as a constellation, his story forever linked to a specific season for generations to come. This stellar timekeeping allowed for a kind of immortality, a way to embed knowledge, values, and identity into a framework so vast it transcended any single human life or even the lifespan of entire dynasties. It was the ultimate expression of planning for a future they would never see, a legacy written in the eternal language of the night sky. In the dense rainforests of Mesoamerica, the Maya civilization achieved a sophistication in timekeeping that remains almost unparalleled in human history. Their understanding of celestial mechanics was so profound that they didn't just create one calendar, they engineered an entire system of interlocking cycles, a complex gearwork of time that wove together the sacred, the practical, and the cosmic into a single, cohesive worldview. At the heart of this system was the Tzolk'in, a 260-day sacred round that remains one of the most enigmatic cycles ever devised. Unlike calendars tied to obvious astronomical phenomena, the Tzolk'in's origin is a mystery. It combined 20-day names with 13 numbers, creating a 260-day permutation that many scholars believe was based on the human gestation period, linking the very cycle of life to the sacred rhythm of time. This calendar governed rituals, divination, and the naming of individuals, deeply embedding itself in the spiritual fabric of daily Mayan life. Running concurrently was the Hob, a 365-day solar calendar that mirrored the agricultural and seasonal year. It was composed of 18 months, each with 20 days, plus a final, abbreviated month of 5 days known as the Wayeb. These 5 days were considered extremely dangerous, a time when the veil between the earthly world and the spirit world was thin, and malevolent forces could cause chaos. People would often stay indoors, avoiding significant activities and conducting rituals to ward off misfortune. The Hob provided the practical framework for society, dictating the timing of planting, harvesting, and civil ceremonies. But the true genius of the Maya was their ability to synchronize these two cycles. The Tzolk'in and the Hob would realign only once every 52 years, a period known as the calendar round. This completion of a full cycle was a moment of tremendous cosmic significance, marked by elaborate ceremonies to ensure the world would continue its journey and not descend into oblivion. For events spanning longer than 52 years, the Maya developed the long count, a linear calendar that placed any given day within a grand, millennia-long timeline. This was the calendar of kings and history, used to record the births, accessions, and great deeds of rulers on stone stelae, ensuring their legacy would be remembered for ages. The long count counted days from a mythological starting point, often correlated to August 11th, 3114 BCE in our Gregorian system. It employed a modified base 20 system, counting days in units of kin 1 day, Uinal 20 days, Tun 360 days, Katun 7,200 days, or roughly 20 years, and Baktun 144,000 days, or nearly 400 years. The completion of a 13 Baktun cycle in 2012 sparked immense global fascination and misunderstanding, illustrating how the Maya conceived of time in vast, epochal stretches far beyond the scope of a single human life. This intricate system was not born from abstract speculation. It was the product of relentless, meticulous observation. Mayan astronomer-priests spent generations carefully tracking the movements of celestial bodies from observatories like the Caracol at Chichen Itza. Their surviving codices, books made of bark paper, are filled with complex tables predicting the cycles of Venus, Mars, and solar and lunar eclipses with stunning accuracy. The Dresden Codex, for instance, contains a Venus table that is accurate to within 1 day in 500 years. These predictions were not mere intellectual exercises, they were central to statecraft and religion. The appearance of Venus as the morning star was associated with war and conflict, and rulers would often schedule military campaigns to coincide with its specific phases, believing the celestial omen would grant them victory. An eclipse was a moment of potential cosmic danger, requiring rituals and offerings to appease the gods and ensure the sun or moon would return. This deep astronomical knowledge was literally set in stone, encoded into the very architecture of their cities. The Pyramid of Kukulkan at Chichen Itza is perhaps the most famous example. During the spring and autumn equinoxes, the setting sun casts a shadow across the northern staircase, creating the undulating illusion of a feathered serpent slithering down from the temple to the earth. This dramatic event, lasting for hours, was a powerful public spectacle that connected the ruler to the divine and demonstrated a masterful command of the cosmos. It was a physical manifestation of the Mayan belief that time was not a linear march but a sacred, cyclical process of creation, destruction, and rebirth. Their calendar was more than a tool for measurement. It was a complete philosophical system, a way of understanding humanity's place within an ordered, predictable, and yet deeply spiritual universe. This incredible drive to build with stone and sky was not unique to Stonehenge or the Maya. Across the globe, from the misty highlands of Scotland to the arid coastline of Peru, ancient cultures embarked on astonishing engineering projects, transforming their landscapes into permanent, open-air observatories. These stone circles and megalithic structures stand as silent testimony to a universal human impulse to pin down the cycles of the cosmos in the unyielding medium of stone. They represent a collective leap of imagination and effort where entire communities dedicated generations to a single goal, making the intangible passage of time something tangible, something you could walk between and touch. In the Outer Hebrides of Scotland, the Callanish stones rise from the peat bog like a petrified forest, their dark Lewisian gneiss slabs arranged in a complex cross-shaped pattern. While less famous than Stonehenge, Callanish possesses an even more intricate celestial alignment. The central monolith and its surrounding circle are precisely oriented to the majestic rising of the full moon every 18.6 years, a cycle known as the lunar standstill. During this rare event, the moon appears to skim along the southern horizon, seeming to dance between the stones before dramatically reappearing, a spectacle that must have held profound ritual significance for the Neolithic people who built it some 5,000 years ago. Similarly, on the other side of the world, in what is now Peru, the enigmatic 13 towers of Chanquillo form an artificial horizon along a desert hilltop. This 2,300-year-old complex functions with the simplicity of a giant stone calendar. From specific observing points, the sun rises and sets at different points along the line of towers throughout the year, with the solstices marked by its position at either end of the array. A person standing at the correct Western observatory could have determined the exact date within a few days simply by noting which tower the sun rose behind. The construction of these sites was a monumental undertaking that speaks volumes about their importance. The massive stones at Callanish, some weighing several tons, were hauled across miles of rugged terrain without the aid of wheels or draft animals. The builders of Chanquillo moved and precisely shaped thousands of cubic feet of rock and earth to create their solar sightlines. This level of effort required more than just a few interested stargazers. It demanded a highly organized society with a shared purpose, specialized knowledge in engineering and astronomy, and a leadership capable of coordinating labor over decades or even centuries. The sheer investment of resources implies that accurate timekeeping was not a mere convenience but an absolute priority, essential for the community's spiritual, agricultural, and social survival. These were not just projects, they were legacies. The function of these places extended far beyond pure astronomy. They were undoubtedly sacred spaces where the celestial and the terrestrial realms met. The dramatic alignment of the sun or moon with specific stones would have been a powerful, awe-inspiring event, transforming an abstract astronomical principle into a visceral, shared experience. This fusion of science and spirituality reinforced the authority of the priest astronomers who could predict these events, and it unified the community through collective ritual. Gathering at a stone circle to witness the winter solstice sunrise was an act of faith and hope, a communal prayer for the sun's return and the rebirth of the land, made all the more potent by the precision of the architecture that made the event predictable. What is perhaps most fascinating is the phenomenon of independent invention. Cultures separated by vast oceans and millennia with no possible contact arrived at strikingly similar solutions to the problem of tracking time. The same fundamental principles using standing stones to mark solstice sunrises or lunar extremes appear in Neolithic Britain, Bronze Age Peru, and Native American cultures of the American Southwest. This global parallel suggests that the drive to understand and measure time is a fundamental part of the human experience, a cognitive leap that arose independently whenever a society reached a certain level of complexity and looked up at the same sky with the same questions. Archaeoastronomers continue to decode these ancient alignments, using modern technology like 3D mapping and computer simulations to confirm the intentionality behind these structures, slowly recovering a lost chapter in humanity's first scientific revolution. Each decoded alignment is a recovered conversation between our ancestors and the universe. But who were the individuals behind these incredible achievements? The construction of megaliths and the prediction of eclipses were not acts of communal guesswork. They required deep, specialized knowledge preserved and advanced by a dedicated intellectual class. In the great civilizations of Mesopotamia, Egypt, China, and Mesoamerica, this sacred duty fell to a unique combination of priest and astronomer. these were not separate roles but a single, powerful identity. Their observatories were temples, their tools were ritual objects, and their data was divine scripture. They were the keepers of time itself, and their authority stemmed from a single, profound ability to predict the seemingly unpredictable motions of the heavens. This expertise required a formidable array of tools and techniques, transforming raw observation into precise science. In Babylon, scholars used simple but highly effective instruments like the gnomon, a vertical stick whose shifting shadow length could mark both the time of day and the passing seasons. Later, more complex devices like the astrolabe would allow them to measure the altitude of stars with remarkable accuracy, but their most powerful tool was the written word. For centuries, Babylonian astronomer-priests meticulously recorded their nightly observations on countless clay tablets, creating the world's first long-term scientific datasets. They noted the positions of planets, the timing of lunar eclipses, and the appearances of comets. This vast archive, preserved in library temples, allowed them to detect patterns and cycles that spanned generations. They could look back through centuries of records and predict a lunar eclipse with confidence, not through magic, but through the accumulated weight of empirical data. In China, a similar tradition flourished, with court astronomers keeping detailed records on silk and bamboo, their annals noting celestial events like guest stars, what we now know as supernova, with painstaking care. The power that came with this knowledge was immense and directly tied to the political structure of the state. A king or emperor derived his legitimacy from the concept of the mandate of heaven, or divine favor, and nothing signaled that favor more clearly than a well-ordered cosmos. The priest astronomer served as the essential intermediary, interpreting the will of the gods through celestial signs. If the astronomer predicted a solar eclipse and it occurred exactly on schedule, it demonstrated the ruler's harmonious relationship with the cosmic order. Conversely, an unexpected celestial event, like a comet or meteor shower, could be interpreted as a dire omen of heavenly displeasure, potentially destabilizing a reign. This gave the astronomer-priests tremendous influence. They held the keys to legitimizing power. An emperor planning a coronation, a general considering a military campaign, or a farmer hoping to plant his crops, all would first consult the celestial calendar maintained by these experts. Their pronouncements on auspicious and inauspicious days shaped the rhythm of entire empires. This role made them the ultimate bridge between two worlds. On one side was the divine, the mysterious realm of gods and cosmic forces that governed human destiny. On the other was the mundane, the everyday needs of agriculture, taxation, law, and social order. The astronomer-priests translated the infinite and terrifying complexity of the cosmos into a practical, actionable schedule for society. They turned the heliacal rising of Sirius into a signal to prepare for the Nile's flood. They transformed the cycles of Venus into a calendar for warfare and diplomacy. They converted the slow precession of the stars into a grand cosmological narrative that gave meaning to human existence. In doing so, they performed the first great act of data science, taking overwhelming natural phenomena and distilling them into usable information. The legacy of these ancient scholars is woven into the very fabric of modern science. Their methods, meticulous observation, long-term record-keeping, and the search for predictable patterns, are the foundational principles of the scientific method. The division of the circle into 360 degrees is a direct inheritance from the Babylonian base 60 number system, developed for their astronomical calculations. Our ability to forecast celestial events years, even centuries, in advance stands on the shoulders of these first astronomers who spent their lives watching the night sky, not for personal gain, but to fulfill a sacred duty to their civilization. They were the original scientists, proving that the universe operates by knowable laws, and that through patience, reason, and dedication, humanity can learn to read them. These intricate systems of stones and stars were never just cold, calculating machines for tracking days. They were the very heartbeat of ancient societies, pulsing with stories, gods, and the deep, rhythmic ceremonies that gave human life its meaning. A calendar was a sacred storybook, its chapters written in the turning of the seasons, its characters the deities who governed the sun, the rain, and the harvest. It provided the stage upon which the great drama of existence, birth, death, renewal, and sacrifice was performed again and again, year after year, binding the community together in a shared understanding of their place in the cosmos. In ancient Rome, the calendar was a complex web of religious obligation and civic duty, a public script that dictated the rhythm of life for every citizen. Specific days were designated for everything from conducting business to honoring the dead, but the most vibrant threads in this tapestry were the numerous festivals, or feriae. Each month was packed with celebrations tied to the agricultural cycle and the pantheon of Roman gods. The Saturnalia in December, for instance, temporarily turned the social order upside down. Masters served meals to their slaves, gambling was permitted in public, and a general atmosphere of merriment and gift-giving prevailed. This wasn't just a winter party, it was a ritualized pressure valve, a scheduled period of controlled chaos that ultimately reinforced the social structure by allowing for its temporary release. Similarly, the Lupercalia in February involved young men running through the streets, striking women with strips of goat hide to promote fertility and purification. A strange rite to modern eyes, but one that connected the community's well-being to specific, calendarically ordained actions. This connection between cosmic cycles and ritual action reaches its most intense expression with the Aztecs of Mesoamerica. Their world view was founded on the terrifyingly fragile premise that the universe required constant nourishment to prevent its collapse into eternal darkness. The sun god Huitzilopochtli needed strength for his daily battle across the sky, and that strength could only be provided by the most precious substance in existence, human blood. The Aztec calendar, a complex interlocking of a 260-day sacred cycle and a 365-day solar cycle, served as a precise schedule for this cosmic maintenance. The timing of ritual sacrifices was meticulously aligned with celestial events. The flowering of a specific plant, the position of the Pleiades star cluster, or the zenith passage of the sun could all signal the need for a ceremony to feed the gods. For the Aztecs, this was not brutality. It was a profound and necessary reciprocity. Their entire civilization, its harvests, and its continued existence depended on this sacred exchange, meticulously managed through their understanding of time. Beyond appeasing deities, these calendrical rituals served a crucial sociological function. They were the primary mechanism for teaching and reinforcing cultural values, history, and law. In pre-literate societies, a ceremony is a living textbook. The annual reenactment of a founding myth during a solstice festival wasn't just entertainment. It was a way to immerse each new generation in the core beliefs of their people. The repetitive nature of these timed events, the same stories told at the same time each year, the same songs sung, the same dances performed, created a powerful sense of continuity and identity. Everyone, from the highest priest to the youngest child, had a role to play, fostering a deep sense of social cohesion and shared purpose. The calendar ensured that this cultural knowledge was not lost but was instead baked into the very rhythm of life, passed down through participation rather than pen and paper. In this way, the abstract, terrifying flow of time was transformed into something manageable and meaningful. The changing seasons were no longer just random shifts in weather. They were the story of Demeter's grief for Persephone, played out in the Greek Eleusinian mysteries. The unpredictable dangers of the sea were given a face in the form of a god like Poseidon, who could be honored with festivals on specific dates to ensure safe passage. Calendars provided a narrative structure that helped people navigate not only the year but the very experience of being human. They answered the profound questions of why we are here and what we should do, turning the relentless tick of a cosmic clock into a guided journey filled with purpose, tradition, and a deep connection to everyone who had come before and everyone who would follow. Even the most brilliantly designed calendars faced a relentless and invisible enemy, the unyielding mathematics of the solar system. The fundamental challenge was simple yet profound. The time it takes for Earth to complete one orbit around the Sun is not a neat, whole number of days. It is approximately 365 and 1/4 days. This tiny fraction, just 6 extra hours each year, might seem trivial, but over time it accumulates into a glaring problem. Imagine a calendar that faithfully counts 365 days every year. After just 4 years, that calendar would be behind by a full day. After 40 years, it would be 10 days out of sync with the actual seasons. A spring festival intended to celebrate the planting of crops would, within a few generations, be occurring in the dead of winter. This gradual misalignment between the calendar date and the astronomical reality is known as drift, and correcting it became one of the most critical puzzles for ancient timekeepers. Long before Julius Caesar turned his attention to the Roman calendar, other cultures had already identified this nagging discrepancy. The ancient Egyptians were among the first to recognize the issue with stunning clarity. Their civil calendar of 365 days was elegant and simple, but their astronomers who meticulously tracked the star Sirius knew it was flawed. They observed that their civic new year slowly cycled through all the seasons over a span of 1,460 years, a period they called the Sothic cycle. They understood the problem but, for reasons lost to history, never officially integrated a correction into their civil administration. Instead, they maintained a separate, more accurate astronomical calendar for religious and agricultural purposes, living with a dual system that highlights the difficulty of implementing such a fundamental reform. The solution that would eventually conquer this drift was the leap year, and its first widespread, systematic implementation is credited to the Roman general and dictator, Julius Caesar. By the time Caesar came to power, the Roman calendar was in a state of utter chaos. The original Roman calendar was a convoluted lunar system that had been poorly maintained for decades, manipulated by politicians for personal gain, and had drifted so far that the harvest festival was falling in the heat of summer. Seeking to assert his authority and bring order to the empire, Caesar consulted the best minds of his day, notably the Alexandrian astronomer Sosigenes. Together, they designed a bold new system, the Julian calendar. This was a radical shift to a purely solar model, with 365 days in a year and a single extra day added every 4 years to account for that missing quarter of a day. This new day was inserted into the month of February, creating what we now know as February 29th. The initial rollout in the year 45 BC was itself a dramatic correction. To force the Roman calendar back into alignment with the seasons, Caesar had to declare that year, known as the Year of Confusion, a whopping 445 days long. While this must have been bewildering for the average Roman citizen, the long-term effect was transformative. For the first time, the Roman world had a stable, predictable calendar that stayed in sync with the seasons without requiring constant political tinkering. The Julian calendar was a monumental achievement that spread with the empire, and would form the basis of Western timekeeping for over 16 centuries. Yet the Julian solution, while brilliant, was just a little too generous. The solar year is not exactly 365 and 1/4 days long. It is about 11 minutes shorter. Those 11 minutes per year add up to roughly one full day every 128 years. Over centuries, this tiny error began to compound. By the late 16th century, the Julian calendar had drifted by about 10 days. The spring equinox, which was used to calculate the date of Easter, was now occurring on March 11th instead of the traditional March 21st. This was a serious problem for the Catholic Church, as the timing of its most important holiday was becoming increasingly disconnected from its astronomical anchor. This final refinement came from Pope Gregory XIII in 1582. Acting on the recommendations of a commission of astronomers, he introduced the Gregorian calendar reform. The fix was twofold. First, to correct the existing drift, 10 days were simply skipped. People across Catholic Europe went to bed on October 4th and woke up the next morning on October 15th. Second, to prevent the drift from happening again, a new, more precise rule for leap years was instituted. A year would be a leap year if it was divisible by 4, unless it was a century year divisible by 100. However, even century years would be leap years if they were also divisible by 400. This is why the year 2000 was a leap year, but the year 1900 was not. This elegant adjustment brought the average length of the calendar year to 365.2425 days, a figure so precise that it will take over 3,000 years for the Gregorian calendar to accumulate a single day of error against the solar year. This relentless pursuit of precision, spanning from the fields of ancient Egypt to the papal courts of Renaissance Europe, stands as a powerful testament to humanity's enduring desire to harmonize our constructed order with the perfect, unwavering rhythm of the cosmos. While the grand stone circles and celestial alignments were busy mapping the year and the seasons, a parallel revolution was happening on a much smaller, more human scale. Ancient societies realized that to truly organize their daily lives, they needed to break time down into even smaller, more manageable pieces. They needed to track not just the turning of the year, but the passing of the hours within a single day. This challenge gave rise to the world's first portable and personal timekeeping devices, tools that moved timekeeping from the monumental and communal into the practical and personal realm. The most widespread of these was the sundial, an elegantly simple device that transformed a stationary shadow into a public clock. The basic principle was timeless. A gnomon, a stick or slanted blade, would cast a shadow onto a flat surface marked with lines indicating the hours. As the sun journeyed across the sky, the shadow would sweep across these markings, providing a clear, visual readout of the time of day. The Greeks and Romans perfected this art, creating intricate, portable sundials made of bronze or even small, pocket-sized versions carved from stone. But their most significant impact was in the public square. Large, ornate sundials were erected in forums and agoras, becoming the central timepieces for entire cities. They allowed for the coordination of markets, the start of legal proceedings, and the gathering of citizens for public announcements. For the first time, urban life could run on a shared schedule, fostering a new sense of communal punctuality and synchronized activity that was essential for the functioning of a complex state. But the sundial had one obvious and significant limitation. It was utterly useless on a cloudy day or at night. To solve this problem, ancient innovators turned to a completely different element: water. The water clock, or clepsydra, meaning water thief in Greek, was a remarkably ingenious solution. It worked on the simple principle of measuring time by the regulated flow of liquid from one container to another. An upper vessel would slowly drip water into a lower vessel, which was marked with graduated lines. As the water level rose, the markings would indicate the passage of hours. The Greeks are renowned for their sophisticated clepsydry, which they used to precisely time speeches in law courts, ensuring each side in a trial had equal opportunity to present its case. This introduced a new concept of fairness measured not by intuition but by objective, quantifiable time. The Chinese took water clock technology to an even higher level of complexity during the Han Dynasty. Their ingenious multi-tiered systems used a series of overflow tanks to maintain a constant water pressure in the supply reservoir, resulting in a fantastically steady and accurate flow. This eliminated the natural slowing that occurred as the water level in a simple clepsydra dropped, creating a much more reliable timepiece. Some of these elaborate Chinese clocks were not just timekeepers but full automatons, incorporating mechanical figures that would ring bells, beat drums, or hold up tablets to announce the hour. This transformed the water clock from a simple measurer into a spectacular public spectacle and a symbol of imperial technological prowess. The societal impact of these devices was profound. They fundamentally changed humanity's relationship with time, segmenting the continuous flow of daylight into discrete, named units, the hours. This granular measurement paved the way for a new regimentation of daily life. Work shifts could be standardized, prayers could be called at specific times, and scientific experiments could be timed with a new level of precision. The water clock allowed time to become a resource that could be measured, allocated, and even wasted, a concept that was entirely new. These tools bridged the immense, awe-inspiring scale of celestial time with the intimate, pressing needs of the human day. They were the critical link between the cosmic calendars that governed empires and the personal schedules that began to govern individual lives, setting the stage for every clock and watch that would follow. This incredible fusion of astronomy and architecture represents one of the most enduring legacies of the ancient calendar builders. They didn't just observe the sky, they physically built its rhythms into their world, transforming temples, pyramids, and even entire cities into permanent, unmovable clocks and calendars. This was architecture as divine science, a way to capture celestial moments in stone and mortar for all eternity. Imagine standing before the great temple of Karnak in Egypt during the festival of Apet. On this specific day, the axis of the temple was perfectly aligned so that the rising sun would send a beam of light deep into the innermost sanctuary, illuminating the statue of the god Amun-Ra. This wasn't a happy accident. It was a meticulously engineered event, a moment of calculated magic where the divine literally touched the earthly realm, reinforcing the pharaoh's role as the intermediary between the people and the gods. The entire temple complex was designed as a cosmic machine, its alignment serving both practical timekeeping and profound spiritual theater. Far across the world, high in the Andes Mountains, the Inca demonstrated a similar mastery of architectural astronomy at Machu Picchu. Here, they didn't just align structures with the sun itself, but with the dramatic natural horizon. The Intihuatana stone, the so-called hitching post of the sun, is the most famous example, but the entire site is a masterclass in landscape timekeeping. Certain windows and doorways in the stone buildings are perfectly framed to highlight specific mountain peaks on the horizon. On the June solstice, the sun would rise directly over one particular peak, signaling the start of the winter solstice and the important Inti Raymi festival. Another peak would mark the December solstice. By using these permanent natural features as their markers, the Inca created a calendar that could never be lost or broken. The mountains themselves became the numbers on their celestial clock, a testament to their deep integration with the environment. This method ensured that even without written records, the critical dates for planting, harvesting, and ceremony would always be knowable to anyone who understood the language of the architecture. The motivation behind these colossal projects was as much about power as it was about precision. For a ruler, the ability to predict and stage these celestial events was a direct source of political authority. When a priest-king could stand before his people and command the sun to rise between two specific pillars or illuminate a hidden altar, he was demonstrating a control over the very fabric of time and the will of the gods. It was the ultimate propaganda, a visible, awe-inspiring demonstration that his right to rule was sanctioned by the cosmos itself. This knowledge was power, often kept secret within the priestly class to maintain their elite status and influence over the ruler and the populace. The calendar, encoded in architecture, became a tool of social control, legitimizing the hierarchy and ensuring the population's activities were synchronized not just with the seasons, but with the state's demands for labor, tax collection, and military service. What makes this architectural astronomy so profound is its permanence and its passive genius. Unlike a water clock that requires refilling or a written calendar that can decay, a stone alignment endures for millennia. It requires no expert to operate it each year. The sun does all the work, faithfully triggering the designed effect season after season, century after century. This was a way to encode critical knowledge directly into the landscape, creating a fail-safe system that could outlast languages, dynasties, and even the civilization that built it. The builders of Karnak and Machu Picchu are long gone, but their calendars still function, still marking the solstices with silent, stone-cold precision. This was timekeeping designed for the ages, a conversation with the cosmos set in stone, ensuring that the essential rhythms of life would never be forgotten. While the Egyptians were perfecting their solar calendar along the Nile, and the Maya were weaving their complex cycles in the rainforests, another civilization in the Fertile Crescent between the Tigris and Euphrates rivers was laying the foundational stones of modern timekeeping through sheer mathematical genius. The Babylonians, inheritors of the even older Sumerian tradition, approached the cosmos not just as priests or storytellers, but as the world's first true data scientists. Their most profound and enduring gift to the world was their unique base 60 numeral system, a choice that might seem arbitrary to us today, but which revealed a remarkable mathematical elegance. Unlike our base 10 system, 60 is a highly composite number, divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This mathematical flexibility made complex fractions and astronomical calculations far simpler to manage, a computational advantage that would echo through millennia and is the very reason we still divide an hour into 60 minutes and a minute into 60 seconds today. This numerical sophistication was put to its ultimate test in their development of an exceptionally precise lunar calendar. Babylonian astronomer-priests, known as letter 1E6 DUPS Hachek A Enuma Anu Enlil, or scribes of the series of Anu and Enlil, dedicated their lives to meticulous observation. Night after night, they tracked the moon's phases, recording their findings on clay tablets with a reed stylus. Their year consisted of 12 lunar months, each beginning not with a calculation, but with the first sighting of the thin crescent moon after its period of invisibility. This required official observers to scan the western horizon at dusk, ready to announce the new month to the kingdom. To keep this lunar calendar in sync with the solar year and the all-important agricultural seasons, they mastered the art of intercalation. Through centuries of accumulated data, they discovered a powerful cycle. Over a period of 19 years, the phases of the moon almost perfectly realign with the solar cycle. This meant that by adding 7 extra months at specific points within that 19-year period, their calendar would remain perfectly synchronized. This metonic cycle, later adopted by the Greeks, remains a cornerstone of lunisolar calendar calculations to this day. The true testament to Babylonian precision, however, lies in their ability to predict celestial events that must have seemed terrifyingly random to other cultures: eclipses. By analyzing centuries of their own observational records, they detected a repeating pattern now known as the Saros cycle. This is a period of approximately 18 years, 11 days, and 8 hours after which the Sun, Earth, and Moon return to nearly the same relative geometry, and a similar eclipse will occur. Their clay tablets are filled with long lists of eclipse possibilities, noting patterns like, on the 14th day of the month, an eclipse is possible, on the 28th it is not. Their predictions weren't always perfect, but their success rate was astonishing for the era. This ability to foresee such dramatic events transformed eclipses from terrifying omens sent by angry gods into predictable, natural phenomena. This was a monumental intellectual leap, moving timekeeping from the realm of myth and superstition into the domain of predictable mathematical science. All of this knowledge was preserved in the world's first great scientific archives, vast libraries of clay tablets baked hard in the sun or kilns, ensuring their survival for thousands of years. These were not random collections of myths, but systematic, organized records of observational data, mathematical tables, and procedural instructions. Tablets like the Mull, a pin series, served as textbooks listing stars, constellations, and their heliacal risings, and providing rules for predicting solstices, equinoxes, and planetary movements. This practice of rigorous, long-term record-keeping is perhaps their greatest legacy. It allowed each generation of scholars to build directly upon the work of their predecessors, creating a cumulative tradition of knowledge that could be verified, refined, and expanded over centuries rather than being lost and rediscovered. This methodology would profoundly influence the later astronomers of Greece and the Islamic Golden Age, who built their own models upon the bedrock of Babylonian data. The Babylonian contribution shows us that the shift from observing patterns to truly understanding them requires more than just looking up at the sky. It requires the patient, painstaking work of writing it all down, crunching the numbers, and trusting the mathematics to reveal the hidden order of the universe. Across the vast expanse of imperial China, the measurement of time was never a simple choice between the sun and the moon. It was a masterful synthesis of both. The Chinese calendar stands as a monumental achievement in lunisolar timekeeping, a sophisticated system that harmoniously wove together the monthly rhythm of the moon with the annual journey of the sun to create a tool that was both agriculturally precise and deeply culturally significant. Unlike purely solar or lunar models, this hybrid approach reflected a core philosophical principle: the balance of complementary forces, the yin of the moon's cycles with the yang of the sun's unwavering path. This was timekeeping as an art form designed to keep human society in perfect sync with the entire cosmos. The immense responsibility for maintaining this celestial harmony fell upon the emperor and his court astronomers. These scholars were not mere technicians, they were high-ranking officials operating from the imperial observatory, and their work was a matter of state security. The concept of the mandate of heaven held that the emperor's right to rule was granted by the celestial powers, and nothing signaled divine approval more clearly than a well-ordered universe. If the court astronomers failed in their duties, if the calendar drifted out of sync with the seasons, leading to a failed harvest, or if they failed to predict an eclipse, it was interpreted as a catastrophic sign that the emperor had lost the favor of heaven. Such an error could legitimize rebellion and plunge the dynasty into chaos. This immense pressure fueled centuries of incredible innovation and meticulous observation, as the accuracy of the calendar was directly tied to the stability of the empire itself. At the heart of this system's practicality were the 24 solar terms known as Jiki. This was the calendar's solar backbone, a breathtakingly precise division of the ecliptic, the sun's apparent path through the sky, into 24 equal segments of 15 degrees each. Each solar term corresponds to a specific astronomical event and, more importantly, to a definitive change in climate and natural phenomena. They have beautifully evocative names like Spring Begins, The Rains, Grain Rain, and Great Cold. A farmer didn't need to know the date. He needed to know when it was time for insects awaken or grain in ear. These terms provided an exquisitely detailed, solar-based agricultural guide that perfectly complemented the lunar months, ensuring that the planting, tending, and harvesting of crops were always timed to the absolute optimal moments in the solar year, regardless of the phase of the moon. Running alongside this annual cycle was a much larger, grander rhythm, the 60-year cycle. This complex period is created by combining two separate cycles. The first is the 10 heavenly stems, which are associated with the 5 classical elements: wood, fire, earth, metal, water in their yin and yang aspects. The second is the 12 earthly branches, each represented by a familiar zodiac animal: the rat, ox, tiger, and so on. By pairing one stem with one branch, you get a unique name like Yang Wood Dragon. It takes 60 such combinations to complete a full cycle before the sequence repeats. This system was used to mark not only years but also months, days, and even hours, creating a complex astrological framework that influenced everything from personal fortune and marriage compatibility to state ceremonies and the naming of eras under an emperor's reign. All of this complex machinery culminates in the most important festival in the Chinese world, the Lunar New Year. This holiday spectacularly demonstrates the lunisolar system in action. Its date is determined by the moon. It falls on the second new moon after the winter solstice, which can occur between January 21st and February 20th. Yet its purpose is to mark a solar event, the end of winter's stillness and the gradual return of yang energy with the approaching spring. The festival is a vibrant tapestry of traditions, family reunions, feasts, the giving of red envelopes, and loud fireworks, all intended to sweep away the old year and welcome the new with prosperity and good fortune. This celebration, along with other moon-based festivals like the Mid-Autumn Festival, shows how the calendar was never a cold, administrative tool. It was the very rhythm of life, a sacred cycle that connected the celestial patterns above to the cultural heartbeat of an entire civilization below. A system so resilient and beautifully crafted that it continues to guide and celebrate lives millennia after its creation. Perched high in the Andes, the ancient city of Machu Picchu seems to float among the clouds, a breathtaking testament to Inca engineering. At its heart, on a sacred platform with panoramic views of the surrounding peaks, stands one of the site's most enigmatic and carefully preserved features, the Intihuatana stone. This intricately carved granite pillar, whose name translates poetically to the hitching post of the sun, was far more than a ritual object. It was the crown jewel of the Inca's astronomical system, a precision instrument designed to capture the sun's journey and anchor the very rhythm of life to the cosmos. The Inca understood that the sun, or in Thai, was the source of all life, but they also observed its seemingly weakening path as it moved toward the winter solstice. They believed this stone, through ceremony and precise alignment, spiritually tethered the sun in place, preventing it from disappearing entirely and ensuring its vital return. The genius of the Intihuatana lies in its multifaceted function. Its four sides are perfectly aligned with the four cardinal directions, while its topmost pyramidal point is carved at an angle that corresponds exactly to the latitude of Machu Picchu. This was no decorative choice, it was a feat of mathematical and astronomical engineering. On the two solstices, the most critical days of the year, the stone transformed into a flawless sundial. At noon during the December summer solstice, the sun stands directly overhead, casting no shadow from the stone's central gnomon at all. It is a moment of perfect vertical alignment, a day of maximum power. Conversely, during the June winter solstice, the shadow cast is at its longest and most pronounced. The priests could read these shadow lengths with incredible accuracy, using them not just to mark the day itself, but to track the sun's gradual strengthening or weakening in the days and weeks that followed. This information was the foundation of the Inca Empire's agricultural and ceremonial calendar. The winter solstice ceremony, Inti Raymi, was the most important event of the year. The successful hitching of the sun meant the promise of another growing season, the security of the food supply, and the reaffirmation of the Sapa Inca's divine connection to Inti. The observations made at the Intihuatana dictated the exact timing for planting potatoes and maize in the intricate terraces that cascade down the mountainside below. It signaled when to move herds of llamas and alpacas to different altitudes and when to begin the harvest. In this way, the stone was the ultimate pragmatic tool, its silent readings directly responsible for the survival and prosperity of the population. What makes this achievement even more remarkable is that Machu Picchu was not an isolated observatory. It was a single node in a vast, empire-wide network of celestial markers. Across the sprawling territory of Tawantinsuyu, the Inca constructed pillars on hilltops, carved sight lines into rock, and designed entire cities with alignments to sunrise and sunset on the solstices. Places like the Temple of the Sun in Cusco and the Solar Observatory at Pisac operated on the same principles as the Intihuatana. To ensure calendar consistency across a realm stretching thousands of miles, the Inca relied on their unparalleled infrastructure, the Quhapac Ñan, a complex highway system, and a corps of highly trained relay runners known as chasquis. These messengers could carry information including the precise astronomical observations from key sites at incredible speeds from one end of the empire to the other, synchronizing ritual and agricultural activities from modern-day Colombia to Chile. This system underscores a profound Inca philosophy, the seamless integration of the celestial, the earthly, and the political. Their timekeeping was not locked away in books or complex codes, it was embedded directly into the landscape itself. By using the immutable positions of mountains, the predictable path of the sun, and the enduring quality of stone, they created a perpetual calendar that could not be lost, burned, or forgotten. The Intihuatana and its sister sites were more than just clocks, they were instruments of unification. They provided a shared, objective reality for millions of people across diverse landscapes and cultures, all under the watchful eye of the same sun, tracked by the same methods, and celebrated in the same ceremonies dictated by the emperor in Cusco. It was astronomy as statecraft, and it held a continent-spanning empire together with nothing but stone and sky. While the sun and moon provided the fundamental rhythms for daily and seasonal life, ancient astronomers soon turned their attention to the wanderers, the planets that traced their own unique and mysterious paths against the backdrop of fixed stars. Among these celestial travelers, one shone with an intensity that captivated cultures across the globe, Venus, gleaming low in the twilight sky as either the morning or evening star. Its predictable yet complex cycle became a powerful temporal marker, deeply woven into the fabric of ritual, warfare, and statecraft. This wasn't merely about adding another clock to the cosmic array. It was about engaging with a more dynamic and potentially dangerous layer of the heavens, one that demanded even greater precision and offered even greater rewards for those who could decipher its code. For the Maya, Venus was far more than a beautiful light. It was a deity known as No-Ek, or the Great Star, and its movements were believed to directly influence the fate of kings and kingdoms. Their astronomer-priests tracked its cycles with breathtaking accuracy, documented in tables within the Dresden Codex that could predict its appearances within a matter of hours over a 500-year span. They understood that Venus completes a cycle from its first appearance as the evening star, through its period of invisibility when it passes behind the sun, to its reemergence as the morning star and back again, in a pattern that takes about 584 days. This Venus round was then synchronized with their sacred 260-day Tzolk'in calendar, creating a larger, more potent cycle that repeated every 37,960 days, or roughly 104 years. The specific phase of Venus was believed to hold immense power, particularly its first appearance as the morning star after a period of being absent from the sky. This event was seen as an omen of strife and instability, a time when the god's malevolent influence was at its peak. Maya rulers, who were themselves considered divine intermediaries, would often schedule military campaigns to coincide with this phase, launching what they believed were Star War attacks against their enemies under the auspices of a vengeful celestial patron. The timing of coronations, sacrificial ceremonies, and important diplomatic missions were all carefully calibrated to avoid the inauspicious periods of the Venus cycle and capitalize on its moments of perceived favor. This practice of planetary timekeeping was equally sophisticated millennia earlier in Mesopotamia. Babylonian astronomers, with their meticulous clay tablet records, also devoted immense effort to tracking Venus, whom they associated with the goddess Ishtar. The Venus tablet of Amasajuka, dating back to the 7th century BC but believed to be a copy of much older observations, records the planet's movements over a 21-year period. For the Babylonians, the celestial world was a direct expression of the god's will, and any unusual planetary behavior, a change in brightness, an unexpected disappearance, or a shift in its path, was interpreted as a critical message. A poorly timed appearance of Venus could be read as an omen forecasting everything from the death of a king and the outbreak of disease to the success or failure of the harvest. The court astronomers, therefore, held tremendous responsibility. Their ability to accurately predict planetary motions allowed the king and his advisors to take prophylactic measures, perform specific rituals to appease the angry gods, or conversely, to seize upon a positive omen to launch a new initiative. Their work was a high-stakes combination of precise mathematical calculation and divine interpretation, where a single miscalculation could theoretically lead to social unrest or a disastrous military decision. Integrating these planetary cycles into an existing calendar system represented a monumental intellectual leap. It required moving beyond the relatively straightforward cycles of the sun and moon to grapple with the more complex, retrograde motions of planets, those periods where they appear to reverse course in the sky before continuing forward. Understanding this apparent backtracking required a more advanced model of the solar system and a deeper commitment to long-term, consistent observation. By doing so, ancient timekeepers were effectively adding a new dimension of fate and nuance to their temporal maps. A calendar now didn't just say, "It is time to plant." It could say, "It is a time of danger, be cautious," or "The gods favor bold action now." This planetary layer made the calendar less of a simple almanac and more of a dynamic guide to navigating a cosmos filled with both benevolent and malevolent forces. This intricate dance with the planets reveals a profound shift in humanity's relationship with time and the cosmos. It shows a move from simply reacting to the basic cycles of light and dark or heat and cold, to actively engaging with a more complex and narrative-driven universe. The predictable yet dramatic cycles of Venus and other planets provided a celestial script for human drama, a story of death, rebirth, conflict, and renewal that played out over years rather than seasons. By meticulously tracking these wanderers, ancient priests and kings believed they could not just measure time, but could align their own actions with the deepest, most powerful currents of fate itself, turning astronomy into the ultimate tool for navigating an uncertain world. Imagine a storm-tossed ship sinking to the bottom of the Aegean Sea around 60 or 70 years before the birth of Christ. For 2,000 years, its cargo lay scattered and silent in the darkness, until sponge divers accidentally discovered the wreck off the coast of the Greek island of Antikythera in 1901. Among the statues and amphorae, they recovered a lump of corroded bronze and wood that seemed so unremarkable it was almost overlooked. It was only years later, as the lump began to crumble apart, that researchers saw it for what it truly was, not a shapeless hunk of metal, but the single most astonishing scientific artifact to survive from the ancient world. We now know it as the Antikythera mechanism, a complex clockwork device of staggering ingenuity that completely rewrites our understanding of Greek technology and their mastery of time. This wasn't a simple sundial or water clock. It was an intricate mechanical computer housing a precise system of at least 30 interlocking bronze gears housed in a wooden case. By turning a hand crank on the side, the user could activate the entire assembly, causing dials and pointers to move across various scales, predicting the movements of the Sun, Moon, and likely the 5 known planets with remarkable accuracy. One dial tracked the 4-year cycle of the Panhellenic Games, the ancient precursor to the Olympics. Another reconstructed the irregular orbit of the Moon, while a sophisticated differential gear, a component whose invention was previously credited to the 16th century, even modeled the phases of the Moon, showing its changing face in a tiny, rotating black and white sphere. This was not a device built by tinkerers. It was the product of a highly advanced, and until now completely unknown, tradition of Hellenistic engineering that seamlessly merged cutting-edge astronomical theory with precision craftsmanship. The mechanism's primary purpose was to serve as a dynamic, portable cosmos, a simulation of the heavens that could calculate the timing of celestial events years in advance. It could predict solar and lunar eclipses, not just giving the date but the exact hour they would occur, and even indicated the characteristics of those eclipses based on ancient Babylonian cycle theories. For a sailor, it could have provided crucial navigational aid by tracking the lunar calendar and the positions of stars. For a philosopher or student, it would have been a breathtaking teaching tool, a physical model of the Aristotelian idea of the celestial spheres, making abstract cosmic principles tangibly clear. For a priest, it could have determined the exact dates of religious festivals tied to astronomical phenomena. It was, in essence, a universe in a box, a manifestation of the Greek belief that the cosmos operated by knowable, mathematical laws that could be replicated and understood through human reason and mechanical genius. The existence of such a device implies so much more than what we hold in our hands. The Antikythera mechanism was found on a merchant ship, not in a royal library or a philosopher's academy. This suggests it was not a one-of-a-kind prototype, but likely a luxury item that was being transported, possibly from a workshop in Rhodes where the astronomer Hipparchus had worked. If such a sophisticated machine could be bought and sold, then there must have been a tradition of crafting these devices, a school of thought and manufacturing that has been entirely lost to history. Its complexity rivals that of 18th century Swiss clocks, yet it was built in the 2nd century before Christ. It forces us to confront a humbling and thrilling possibility that the peak of ancient Greek mechanical science may have been as advanced as the European Renaissance, and that this entire branch of technology was simply erased by the passage of time, the burning of libraries, and the sinking of ships. This incredible artifact does more than just surprise us with ancient ingenuity. It fundamentally bridges two worlds of timekeeping we have explored separately. On one side, we have the monumental stationary calendars of Stonehenge and the pyramids, great architectural alignments fixed to the landscape. On the other, we have the personal, portable timekeepers like sundials and water clocks that mark the hours of the day. The Antikythera mechanism sits gloriously in the middle. It possesses the predictive power and cosmic complexity of the grandest stone observatories, yet it is all miniaturized into a device you could hold in your arms. It represents the ultimate fusion of the monumental and the personal, proving that the ancient drive to understand time was not just about building temples to the sky, but about capturing the very mechanics of the universe in a machine of breathtaking beauty and intelligence. Long before the first stone was set at Stonehenge or the first Babylonian astronomer tracked the path of Venus, humanity's original calendar was written not in the stars, but in the living world all around us. This was a timekeeping system woven from the flight patterns of birds, the blooming of specific flowers, the rutting seasons of great herds, and the run of fish upriver. It required no monuments, no mathematics, no specialized priestly class, only a deep, intimate, and attentive relationship with the local environment. For countless generations of early humans, this phenological knowledge, the study of cyclic and seasonal natural phenomena, was the difference between survival and starvation, making the natural world the first and most universal calendar humanity ever knew. This profound connection to nature's rhythms is not a relic of the distant past. It remains a vibrant and essential part of many indigenous knowledge systems today. Numerous Native American tribes, for instance, have traditionally used and continue to honor calendars based on the moon, but each lunar month is named not by a number, but by the most defining natural event of that period. The Lakota people might recognize the moon of popping trees for January, when the cold makes the trees crack, or the moon of the red grass appearing for the early spring. The Arapaho calendar marks the arrival of the moon when the geese lay eggs, or the moon when the alligator eggs hatch. These are not poetic metaphors, they are precise operational indicators. When the salmonberry blossoms appear on the northwest coast, it signals that the herring are running and it is time to put out fishing nets. The first call of the swallow signifies the final retreat of winter frosts and the safe time to begin planting certain crops. This knowledge creates a resilient, hyper-localized timekeeping system perfectly adapted to a specific ecosystem, one that automatically adjusts for annual variations in climate that would throw a rigid, numerical calendar into disarray. The transmission of this intricate environmental wisdom represents one of humanity's oldest and most sustainable educational traditions. This vast library of knowledge was not stored in books or encoded in stone, but carried in the memories and practices of elders, hunters, farmers, and storytellers, and passed down orally through generations. A grandparent would teach a child which specific mushroom appeared after the first autumn rain, or how the changing thickness of a muskrat's fur predicted the severity of the coming winter. This was knowledge earned through a lifetime of careful observation and lived experience, a continuous dialogue with the land where every plant, animal, and weather pattern was a word in a seasonal story. This method of learning fostered not just memorization, but a deep, intuitive understanding of ecological relationships and interconnections, teaching each new generation to see the environment as a complex, communicative web of which they were an integral part. This approach to time fostered a fundamentally different relationship with the natural world, one rooted in reciprocity and sustainability rather than dominion and extraction. When your calendar is the arrival of the bison or the ripening of the acorns, your well-being is directly tied to the health of those species and their habitats. You are incentivized to protect them, to harvest mindfully, to ensure the cycle continues unbroken for generations to come. This stands in stark contrast to a purely numerical calendar, which can create an abstract, disconnected sense of time, separate from the ecological realities that ultimately support all life. A natural calendar inherently teaches balance and restraint. You only take what you need when the time is right, because you understand that your future survival depends on the abundance of the next cycle. This intuitive, earth-based timekeeping represents the most democratic and accessible form of calendar ever devised. It required no advanced technology, no social hierarchy, and no centralized authority. Anyone, regardless of their status, could learn to read the signs if they paid close enough attention. It was a calendar that belonged to everyone and no one, a shared understanding born from collective life in a particular place. While the megalithic builders and astronomer-priests were developing spectacularly complex systems to reach for the cosmos, the vast majority of human communities were simultaneously perfecting this quiet, grounded science of reading the book of nature, proving that the most advanced technology for living in harmony with time might not be found in gearwork or stone alignments, but patient, humble act of observing a single flower as it opens to the sun. Yet for all the power of oral tradition and architectural encoding, there was a limitation, a generational game of telephone where subtle errors could creep in, and complex mathematical patterns spanning centuries could be difficult to transmit with perfect fidelity. The true quantum leap in humanity's ability to master time arrived with the invention of writing. This was the moment when observation could be frozen, when data could be stored, and when knowledge could become cumulative rather than cyclical. Suddenly, a priest astronomer in Babylon didn't have to rely solely on what his teacher told him. He could pull down a clay tablet from the library shelf and read the precise records of his predecessor from 200 years prior, seeing for himself how the planet Venus had moved on a specific night. Writing transformed timekeeping from an art passed down through memory into a true science, built on a permanent foundation of recorded evidence. The mediums for this knowledge were as diverse as the cultures themselves, each uniquely suited to its environment. In the fertile river valleys of Mesopotamia, scribes used a reed stylus to press wedge-shaped marks into soft clay tablets, creating the cuneiform script that recorded centuries of celestial omens and planetary positions. These tablets, once baked hard in the sun or a kiln, became virtually indestructible, creating a vast and durable archive of astronomical data. Across the world, the Maya crafted books known as codices from the beaten bark of the fig tree, coated with a thin layer of lime stucco to create a smooth white writing surface. Their scribes, members of the elite class, used fine brushes to paint intricate glyphs in brilliant red and black inks, detailing the complex cycles of Venus and tables for predicting eclipses with stunning accuracy. In China, court astronomers brushed characters onto bamboo slips or silk scrolls, creating annals that noted the appearance of guest stars, sudden, temporary bright points we now know were supernovae, and meticulously tracked the motions of the heavens as a duty to the emperor. Each of these writing systems became a vault, safeguarding the most precious commodity a civilization could possess, long-term knowledge. This ability to preserve information across generations unlocked the potential for cumulative learning, the engine of scientific progress. A single lifetime is too short to detect many of the sky's most important cycles. The subtle precession of the equinoxes, for instance, shifts the stellar background by just 1 degree every 72 years, a change imperceptible to any individual. But with written records, a Babylonian scholar could compare his observation of the spring equinox with a tablet from 3 centuries earlier and detect that the sun was no longer rising in the same constellation. This long-view perspective allowed for the discovery of complex cycles like the Saros, which predicts eclipses, or the Metonic cycle, which synchronizes the sun and moon. Each generation could stand on the shoulders of the last, checking previous predictions against new observations, refining their models and correcting errors. The calendar was no longer a static tradition. It was a living, evolving project, constantly being improved upon thanks to the meticulous logs of the past. Beyond mere data storage, these written records served a deeper, unifying purpose. They embedded timekeeping into the very legal and religious core of society. A king's claim to the throne was often validated by astronomical records that showed his coronation occurred under auspicious celestial signs. Law codes, like the famous Code of Hammurabi, were steeped in the language of divine order, an order reflected in the predictable movements of the heavens. Religious texts prescribed rituals for specific calendar dates, and the authority to declare those dates correctly was a source of immense power for the priestly class. The written calendar became the official, immutable script for the state, dictating the timing of tax collection, military campaigns, and sacred festivals. It was the framework that held the entire social and cosmic order together, and its keepers were among the most influential people in the ancient world. This makes the tragic loss of such records all the more devastating to contemplate, and no example is more poignant than the burning of the Library of Alexandria. This great institution was not merely a repository of scrolls. It was the beating heart of the classical world's intellectual ambition, a center that aimed to collect all known knowledge. Within its walls likely resided countless astronomical treatises, the original observations of Babylonian stargazers, the geometric models of Greek astronomers, and the celestial lore of Egyptian priests. The library's destruction, a slow decline over centuries through multiple fires and conflicts, represented an incalculable loss. Generations of painstaking observation, brilliant deduction, and hard-won knowledge simply vanished into smoke. This catastrophic event set Mediterranean astronomy back by centuries, forcing later scholars to rediscover truths that had already been known, a stark reminder that the thread of scientific progress is fragile and that writing alone is not enough, it must also be preserved. The story of ancient timekeeping is thus also a story of loss and recovery, a testament to the fact that our current understanding of the cosmos rests on a fractured and incomplete foundation, making the records that did survive all the more precious. Now, let's shift our perspective from the stationary observatories and written records to a world where the calendar had to be carried in the mind, where timekeeping became as fluid and dynamic as the ocean itself. For the Polynesian and Viking navigators who dared to cross the world's greatest oceans, the concept of a calendar was not etched in stone or written on a page. It was a living, breathing mental construct, a sophisticated blend of astronomy, environmental science, and memory that allowed them to conquer the trackless sea. Theirs was a timekeeping of motion, a system that seamlessly integrated the passing of seasons with the specific celestial patterns visible from the ever-shifting deck of a vessel, proving that humanity's quest to master time could travel anywhere. The Polynesian voyagers of the Pacific Ocean achieved what many considered impossible. the settlement of thousands of islands scattered across millions of square miles of open water, from Hawaii to New Zealand to Easter Island. They did this without compasses, sextants, or maps as we know them. Instead, they developed a star compass, a mental map of the heavens divided into 32 directional houses. Each house was defined by the rising and setting points of key stars and constellations. A master navigator, or PWO, would know that steering toward the point where the star Arcturus rose would eventually lead to the Hawaiian Islands, while keeping the Southern Cross off the port stern would guide them toward Tahiti. But this was not a static map, it was a calendar in motion. They knew that as the year progressed, different stars would become the guiding lights for the same route. A journey undertaken in one season would use a completely different set of celestial markers than the same journey months later. Their calendar was this entire mental catalogue of stellar paths, knowing which star would be where at what time of year, and how that information changed with latitude. Their genius extended far beyond the stars. They were master readers of the ocean itself, using its rhythms as a temporal guide. They memorized the complex patterns of ocean swells, massive, rolling waves generated by distant weather systems and planetary forces that remain constant for long periods. By feeling the direction of these swells through the hull of the canoe, a navigator could maintain course even on overcast nights when the stars were hidden. They observed the specific flight paths of birds, knowing that certain species would fly out to sea to fish at dawn and return to land at dusk, revealing the direction to islands far beyond the horizon. They could detect the subtle loom of greenish light over distant lagoons reflected on the underside of clouds, and even sense changes in the ocean's salinity and temperature. All of these environmental clues were tied to seasonal patterns, creating a multi-layered, dynamic calendar that provided constant feedback on their position and progress through both time and space. Meanwhile, in the stormy North Atlantic, the Vikings were developing their own formidable methods of celestial wayfinding. Aboard their sleek longships, they too relied on the sun and stars, but they also used a unique tool shrouded in legend, the sunstone. While no such navigational instrument has been recovered from an archaeological context, sagas describe a crystal, likely a piece of cordierite or Iceland spar, that could pinpoint the position of the sun even through thick cloud cover or the twilight of the polar summer. By rotating the crystal until it achieved a specific polarization of light, a navigator could locate the hidden sun with remarkable accuracy. This, combined with their own deep knowledge of stellar markers and the migratory routes of whales, allowed them to traverse from Scandinavia to Iceland, Greenland, and even the shores of North America. Their sailing schedules were dictated by these celestial and environmental calendars, waiting for the specific time of year when the pack ice would retreat and the North Star would be positioned correctly to guide their westward expansion. The training required to master this knowledge was a lifelong endeavor, a profound embodiment of information passed orally from one generation to the next. Polynesian navigators began their education in childhood, learning through chants, stories, and intricate stick charts that modeled the interaction of ocean swells and islands. This knowledge was not abstract, it was felt in the body, a kinesthetic understanding of the sea's rhythm that took decades to perfect. This was the ultimate portable calendar, a system that could not be lost in a shipwreck or stolen by an enemy. It resided entirely within the mind of the navigator, making him the most vital and respected member of any voyage. He was the living repository of time and space, the human embodiment of a clock, a compass, and a map all in one. This incredible intellectual achievement fundamentally expanded the human horizon. These seafaring calendars were not merely for subsistence. They were the engines of exploration, trade, and colonization on a grand scale. The Polynesian expansion across the Pacific is one of the greatest voyages of discovery in human history. all guided by this sophisticated understanding of time and position. The Viking networks of trade and settlement stretched across continents, connecting cultures and reshaping history. Their methods demonstrate that timekeeping was never solely the domain of settled, agricultural societies. It could be just as complex, precise, and vital for nomadic explorers, providing a flexible, adaptive framework that moved with the people, turning the entire globe into a knowable and navigable space. By the late 16th century, a problem that had been ticking away for over a millennium and a half had finally become impossible for the Catholic Church to ignore. The Julian calendar, a revolutionary system in its time, had slowly but surely drifted out of sync with the actual solar year. That tiny, 11-minute annual error had accumulated into a 10-day discrepancy. The spring equinox, the celestial anchor used to calculate the most important date in the Christian liturgical year, Easter, was now occurring on March 11th instead of the traditional date of March 21st. This was far more than a bureaucratic inconvenience. For a church that derived its authority from its connection to divine order, this misalignment between the heavens and the human calendar was a profound theological and practical crisis. Easter, a movable feast intended to be celebrated on the first Sunday after the first full moon following the spring equinox, was slowly migrating into the summer. The very rhythm of religious life was coming unmoored. Pope Gregory XIII, a reform-minded pontiff, took decisive action. He assembled a commission of renowned astronomers, mathematicians, and clergymen, including the brilliant Jesuit Christopher Clavius, to solve the problem once and for all. Their task was to design a new calendar that would not only correct the existing error but also prevent it from happening again. The solution they devised was both elegantly simple and breathtakingly bold. First, to reset the clock, 10 days were simply erased from existence. By papal decree, the day after October 4, 1582, would be October 15th. This immediate, surgical correction realigned the calendar with the seasons in one dramatic stroke. Imagine the confusion for the average person across Catholic Europe, going to bed on one date and waking up to find a week and a half had vanished overnight. Birthdays, contracts, and rent payments were all suddenly thrust into a new temporal reality. But the true genius of the Gregorian reform lay in its long-term fix for the leap year system. The Commission understood that the solar year is not 365 and 1/4 days long, but slightly less. Their new rule was a masterpiece of precision. A year would be a leap year if it was divisible by 4, unless it was a century year not divisible by 400. This meant that the years 1700, 1800, and 1900 were not leap years, even though they are divisible by 4, but the year 2000 was. This adjustment brought the average length of the calendar year to 365.2425 days, a figure so astonishingly close to the true solar year that it will take over 3,000 years for the error to accumulate to a single day. This was not a guess, it was the culmination of centuries of astronomical observation, from the Babylonians to the Greeks to the Arabic scholars whose data the Commission carefully studied. The implementation of this new calendar, however, was a stark reminder that timekeeping is never purely a scientific matter. It is deeply intertwined with politics, power, and culture. Catholic nations like Spain, Portugal, and Italy adopted the new calendar immediately on the Pope's command, but Protestant and Orthodox nations, deeply suspicious of anything emanating from Rome, resisted fiercely. They saw the Gregorian calendar as a papal plot and refused to comply, leading to a bizarre period in European history where travelers could effectively lose or gain 10 days simply by crossing a religious border. Great Britain and its American colonies did not adopt the change until 1752, by which time the discrepancy had grown to 11 days. The transition there was met with public protests, with people demanding the return of their lost days. Russia held out until after the Bolshevik Revolution, adopting the calendar in 1918, which is why the event known as the October Revolution actually occurred in November according to the Gregorian system. This slow, fractured rollout shows how a unified global time frame is a surprisingly modern invention, one that required not just scientific agreement but eventually economic and diplomatic pressure to become universal. The successful global adoption of the Gregorian calendar represents the final, mature flowering of an ancient endeavor that began with the first stone circles and celestial observations. It is a direct descendant of the Egyptian solar year, the Babylonian math, and the Julian reform, a system built upon millennia of human curiosity and intellectual struggle. It created, for the first time, a truly global framework for synchronizing time, which became the absolute bedrock of the modern world. International trade, scientific collaboration, diplomatic treaties, and global travel all rely on this shared understanding of the date. It is the invisible grid upon which our interconnected civilization is built. Yet, even this near-universal system has not erased older traditions. Many cultures and religions, from Judaism and Islam to China and India, maintain their own ancient calendars for cultural and religious purposes, creating a rich, layered experience of time where the global and the local, the secular and the sacred, continue to coexist. The Gregorian reform stands as a powerful testament to humanity's enduring quest for order, a project that began with our ancestors gazing at the heavens and culminated in a calendar precise enough to coordinate the entire world. While the steady cycles of the sun and moon provided the predictable rhythm of daily life, the ancient sky was also capable of delivering moments of sheer, terrifying spectacle, events so dramatic they seemed to shatter the natural order. A sudden darkness at noon as the sun was devoured by an invisible monster, or the appearance of a ghostly, bearded star streaking across the heavens, these were not part of any normal calendar. Eclipses and comets were the ultimate wild cards, universally interpreted across cultures as direct messages from the gods, urgent omens that demanded interpretation and action. Ancient timekeepers, therefore, faced a critical challenge: how to incorporate these terrifying, unpredictable events into their understanding of an orderly cosmos. Their ingenious solution was to use their growing astronomical knowledge not to prevent these events, but to predict them, thereby transforming paralyzing fear into a powerful tool for foresight and control. In the court of the ancient Chinese emperors, the role of the court astronomer was one of immense pressure and prestige. The Chinese believed in the concept of the mandate of heaven, where the emperor's right to rule was directly tied to celestial harmony. An unexpected event like a solar eclipse was interpreted as a severe warning that the emperor had lost the favor of the heavens, potentially legitimizing rebellion. This made accurate prediction a matter of dynastic survival. Through meticulous record-keeping on bamboo and silk, Chinese astronomers had, by at least the Han Dynasty, deduced the cycle of eclipses. They understood that eclipses occur in patterns now known as Saros cycles, which repeat approximately every 18 years. The ability to anticipate an eclipse allowed the emperor and his court to stage a carefully managed response. As the predicted time approached, the emperor would perform rituals of atonement, and the entire court would make a tremendous noise, beating drums and shooting arrows into the sky to fight off the dragon they believed was consuming the sun. When the sun inevitably returned, it was not a cause for panic but a public relations triumph. a demonstration that the emperor's rituals had restored cosmic order and reaffirmed his divine mandate. Similarly, in Mesopotamia, the cuneiform tablets of Babylonian astronomer-priests are filled with hundreds of years of celestial observations, all dedicated to discerning the will of the gods. They saw the sky as a giant divine text, and events like eclipses were particularly potent sentences. A lunar eclipse might be interpreted as a sign of danger for the king, while a solar eclipse could portend the death of a monarch or a great plague. But like their Chinese counterparts, the Babylonians moved beyond superstitious reaction. Their extensive archives allowed them to identify patterns and create mathematical schemes for prediction. The famous Venus tablet of Amasajuka and other compilations like the Enuma Anu Enlil series served as reference manuals for generations of priests. By the middle of the first millennium BCE, they could predict lunar eclipses with a high degree of accuracy. This predictive power was a profound source of social and political authority. A priest who could warn the king of an impending omen enabled the state to take prophylactic measures, such as installing a temporary substitute king to bear the brunt of the bad fortune, thereby protecting the realm and the true ruler. The appearance of a comet, with its sudden and unpredictable arrival, was perhaps even more frightening than an eclipse. Unlike the cyclical darkness of an eclipse, a comet was a new, unknown, and often long-lasting phenomenon. The Romans saw comets as harbingers of revolution and death, often linking them to the fall of emperors or the outbreak of civil war. The Bayeux Tapestry, centuries later, would famously depict Halley's comet hovering over the court of Harold Roman II, signaling the divine disapproval that would culminate in his defeat at the Battle of Hastings. In these cases, the comet's power lay in its unpredictability. It could not be easily integrated into a cyclical calendar, so its appearance was often retrofitted into historical narratives. After a momentous event occurred, people would look back and point to the comet as the sign that had foretold it all along, weaving these rare occurrences into a tapestry of meaning and destiny. This practice of recording these portents created a new dimension for the calendar itself. Beyond marking the passage of days and seasons, it became a repository of collective memory and meaning. Annals and chronicles from cultures around the world are punctuated with entries that note these celestial wonders alongside reports of battles, the deaths of kings, and natural disasters. A single entry, "In this year a comet was seen," served as a powerful bookmark in history, a shared reference point that everyone understood carried immense weight. The calendar was no longer just a practical tool for agriculture. It was becoming a historical document, a timeline of divine intervention that helped a culture understand its own story. It provided a framework for explaining why things happened, turning chaotic events into a narrative with cause and effect, guided by the gods above. This omen-based approach to timekeeping reveals a profound psychological dimension to humanity's relationship with the cosmos. The deep-seated fear elicited by a solar eclipse or a comet's tail speaks to a fundamental human need to find order in chaos, to believe that even the most terrifying events are part of a larger, intelligible plan. By striving to predict these phenomena, ancient astronomers were not just doing science, they were engaged in a form of cosmic therapy for their entire culture. They were providing reassurance that the universe, though sometimes frightening, was ultimately knowable. The ability to forecast an eclipse and then witness it unfold as predicted was the ultimate proof that the gods were communicating through a decipherable code rather than acting out of random wrath. This transformed the calendar from a mere tracker of time into the most powerful book of divination ever created, a tool that could read the will of the heavens and, in doing so, offer a precious and powerful thing: peace of mind. Every single day, we live by a schedule built on foundations laid thousands of years ago. The 7-day week you meticulously plan around, that's a direct inheritance from the Babylonians, who revered the 7 celestial bodies they could see with the naked eye: the sun, the moon, Mars, Mercury, Jupiter, Venus, and Saturn. They dedicated each day to one of these planetary deities, a tradition so powerful it was adopted by the Romans and eventually spread across the globe. Our 60-minute hour and 60-second minute, that's another Babylonian gift, born from their ingenious base 60 mathematical system, which made complex astronomical fractions so much easier to calculate. Even the names of our months whisper of ancient Rome, from January, named for the two-faced god Janus who looked to the past and future, to July and August, immortalizing the Caesars Julius and Augustus. Our modern timekeeping is not a recent invention. It is a living museum of human history, every tick of the clock an echo of a Babylonian mathematician or a Roman emperor's decree. This ancient legacy extends far beyond the names on a calendar. The very principles that allow us to launch probes to Mars and synchronize global financial markets were first discovered by these early sky watchers. The concept of leap years, which keeps our seasons in place, was a Roman reform built upon Egyptian observations. The meticulous tracking of planetary cycles, a specialty of the Maya and Babylonians, is the bedrock of orbital mechanics used by NASA today. When the Perseverance rover lands on Mars, its mission is timed using complex celestial algorithms that are the direct descendants of the methods used to predict an eclipse over Babylon. Our understanding of vast cosmic cycles, like the precession of the equinoxes that takes 26,000 years to complete, was first noted by ancient astronomers like Hipparchus, who had nothing but his eyes and generations of recorded data. The tools have changed from stone circles to supercomputers, but the fundamental quest to measure, predict, and understand our place in the cosmos remains unchanged, a thread of curiosity stretching back to the very dawn of civilization. In our globalized world, we often operate on a single, standardized Gregorian calendar, but this is just the top layer of a rich, complex tapestry of time. For billions of people, ancient calendars continue to define the most important moments of their lives. The Hebrew calendar, a lunisolar system with deep roots in antiquity, determines the dates of Rosh Hashanah, Yom Kippur, and Passover, connecting Jewish communities across the world to a rhythm that is thousands of years old. The Islamic calendar, a purely lunar system, marks the holy month of Ramadan, which migrates through the seasons, offering a different spiritual experience each year. In India, the diverse regional calendars dictate the timing of festivals like Diwali and Holi, while China continues to celebrate its Lunar New Year based on the same principles of celestial harmony that guided its emperors. This creates a beautiful, layered experience of temporality, where a person might work a Monday to Friday week, celebrate Christmas on December 25th, and also observe holidays that float according to a completely different celestial logic, living simultaneously in multiple streams of time. This enduring influence leads us to a profound realization. Time itself is a human construction. There is an objective, astronomical reality, the Earth's rotation on its axis and its orbit around the Sun, but how we choose to segment, name, a ND Chinese letter to that time is entirely a product of our cultures, our histories, and our collective imaginations. A week is 7 days long not because of a law of physics, but because the Babylonians found spiritual significance in the number 7. Our year starts in the dead of winter because of Roman political decisions, not celestial necessity. This means our relationship with time is not fixed. It is fluid and shaped by story. Understanding that these systems have a history, that they were built by people trying to make sense of their world, allows us to see our own schedules and deadlines not as immutable facts of nature, but as part of a long, ongoing conversation. It enriches our daily lives, adding depth and meaning to the simple act of glancing at a clock or circling a date, reminding us that we are participating in a project that began when the first human looked up at the sky and wondered. From the silent, imposing stones of Stonehenge to the intricate gearwork of the Antikythera mechanism, the legacy of these ancient calendar builders is not confined to history books. It is etched into the very architecture of our modern lives. Every time you glance at your phone to check the date, plan a meeting for next week, or celebrate a birthday, you are participating in a system crafted over millennia by countless curious minds staring at the same sky. The 7-day cycle structuring our work and rest, the 60 minutes in every hour, even the extra day we add every 4 years, these are all direct gifts from Babylonians, Egyptians, and Romans, a continuous thread of human ingenuity connecting their world to ours. Their monumental achievement was to transform the overwhelming, chaotic flow of natural events into a structured, predictable order, creating the shared temporal framework that made civilization itself possible. This profound legacy extends far beyond the confines of our wall calendars and digital planners. The very spirit of their endeavor, the relentless curiosity to observe, the collaborative effort to build, and the intellectual bravery to seek patterns in the cosmos laid the essential groundwork for modern science. The meticulous, long-term data collection of Babylonian astrologers established the principles of empirical observation. The mathematical models developed to predict planetary motion became the precursors to orbital mechanics, the very science that allows us to land rovers on Mars and send probes beyond our solar system. These ancient innovators were the first physicists, the first engineers, and the first astronomers, proving that through careful observation and reasoned deduction, humanity could not only understand the universe but also weave its rhythms into the fabric of daily life, creating a harmony between the celestial and the terrestrial. In our contemporary, hyper-connected world, where time is often a source of stress, a resource to be optimized, a deadline to be met, the perspective of these ancient cultures offers a powerful invitation to reconnect with a deeper, more meaningful rhythm. They understood time not as a number on a clock, but as a story. It was a narrative woven from the changing seasons, the cycles of growth and harvest, the sacred ceremonies that honored the gods and united the community. Their calendars were not tools of efficiency but of meaning, designed to connect human existence to the grand, timeless narrative of the cosmos. In a sense, they were reminding themselves, and now us, that we are part of something vastly larger than our individual schedules. So the next time you feel the pressure of the clock, take a moment to step outside and look up, gaze at the moon, trace the path of the sun, or find a familiar constellation. In that simple act, you are sharing a moment with every one of those ancient sky watchers, from the priest at Karnak to the navigator on the Pacific. You are participating in humanity's oldest and most universal quest to find our place in the grand tapestry of time. Their story is ultimately our story, a testament to the fact that our greatest innovations are born from collaboration, curiosity, and the simple, profound act of looking up at the sky in wonder. We would love to hear how this journey through ancient time has resonated with you. Does your culture have unique ways of marking time? Have you ever visited a site like Stonehenge or Machu Picchu and felt that connection to the past? Share your experiences and reflections in the comments below. And if you enjoyed unraveling this mystery with us, be sure to subscribe and hit the bell so you don't miss our next exploration into history's greatest puzzles. After all, as these ancient masters showed us, time is the most fascinating story ever told.